Hello everyone, my name is Brian Cooper and I represent Cooper Historical Windows and Liberty Restoration Glass Products. Today's webinar is a discussion about closing the gap between historical accuracy and energy efficiency in historical windows. So let's start off by talking a little bit about historical accuracy. As a craftsman who's worked in the restoration industry for over 40 years, we always found it a challenge to find an architectural millwork shop that was willing to reproduce and build and capture the historic details needed to build historically accurate sash and windows for high quality restoration projects. Many of our restoration projects involved dismantling ancient structures, 17th, 18th, and 19th century structures that were slated for demolition. The process of dismantling included numbering, measuring, and photo documenting historic buildings prior to the dismantling. These projects were labor intensive, so in the end, the windows had a huge impact in the correct look for the period. In some cases, we were fortunate enough to find the original sash. Since nothing was ever discarded in the 18th century, we would often find many of the original sash repurposed, back in a new barn, a corn crib, a carriage shed. Often the attic sash were never changed out for the new, brighter 6/6 because it was an unnecessary expense. These were great finds because we could see which species was used. Was the glass 6 by 8 inches or 7 by 9? A fact that helped date the windows. We could see what paint colors had been used, the width of the muttons and the profiles, what molding plane was used to profile the stiles, rails, and muttons. We could analyze how the mortise and tenons were created. Were the tenons on the upper rail of the lower sash a through tenon? Were they wedged? All of these details were carefully documented and shop drawings were created. We would simply reverse engineer the joinery. Whether you were restoring the original sash or replicating sash, we would always use repurposed vintage glass. In new sash, this gave our windows a warm historical look. New glass just didn't seem appropriate. In restoring old sash, it felt right to use vintage glass to replace broken or new panes of glass. With the growth and popularity of modern replacement sash, a lot of old houses disposed of their original sash in hand-blown glass in favor of new energy-efficient vinyl windows. We would reach out to those contractors and buy the old glass from them just to harvest the glass. Over time, we set up our architectural millwork facilities to make the correct windows to our high standard. We made all of the correct and accurate cutters to match the molding profiles and joinery originally made by hand using hand planes of a time gone by. We began to get involved in much more complicated window projects, resourcing the right materials for the job. In some cases, it meant trying out different species that had better long-term attributes. We looked at different paints, gluing, different joinery. All those different elements were analyzed and carefully reintegrated into our overall design concept. I'd like to talk a little bit about the history of glass here in the United States. We were always compelled to try and find original vintage glass for all of our SAS projects in an effort to make the windows as historically accurate as possible. There's just something about wavy glass that ties us to our past. The 18th century glass was referred to as crown glass and was the most prized of all because it was hand blown and had the circular lines in it as a result of the spinning process that was used to expand the glass mandrel. It was spun until the glass was the right thickness, and this was done using a pontil or blowpipe to first blow the molten glass bubble. Then a second pontil or punty was attached to finish the process. This mark or scar left from the pontil was the earmark for what is known as today's bullseye glass. At the time, bullseye glass was considered defective because of the extra waviness and the scar left from the pontil, and it was used over doors and transoms, really basically just to let light in. Today, the 18th century bullseye glass is cherished, rare, and expensive, should you be lucky enough to even find some. Crown glass was available in the 18th century in a 6 by 8 inch pane size, and the glass determined the size of the sash and the overall size of the window. In the latter part of the 18th century, glass became slightly larger. From 6 by 8, it went up to 7 by 9 inches, which, although that doesn't sound like a large increase, it meant a 20% increase in natural light. This was a big increase in a society that had no artificial light to speak of. The candles in the 18th century were not great. They were more akin to lighting a stick of bacon on fire. They were very difficult and the wicks didn't self-trim, so candles were not a big deal. And so we would refer to life in the 18th century as can to can't. In other words, you would work from the first light of dawn until the sun set and you couldn't see anymore. That is why whitewash and plaster surfaces were so important, to add bright reflective surfaces wherever possible in an otherwise dull environment. The next breakthrough in making glass was the development of cylinder glass, first seen around 1800. There were several variations on how this glass was produced. In some cases, a bubble was blown and glass blowers would swing the hot glass back and forth in a pit to elongate the bubble into a bottle or a cylinder. The most popular way was to blow glass into a cylindrical mold. This gave continuity to the process, and 6-foot to 10-foot cylinders were made. These long cylinders would have the ends cut off square to the cylinder, and then the cylinder was scored lengthwise and placed back into an open door furnace. The score mark was cracked and the glass would open up, and if everything went well, that cylinder would lay down and form a piece of glass. This was the beginning of larger and larger panes of glass, a far cry from the 6 by 8 inch crown glass of the 1700s. Once larger panes of glass became available, the size of windows could also grow relative to the glass. So the 8 by 12 pane came along, and that allowed for a 6/6 to replace the 12/12. These windows had a lot less wood blocking the incoming light and offered much brighter environments. Eventually, the glass was big enough that the 1/1, or the clear view, was born. No muttons in the view, and even more sunlight could enter the home or business. Today, we take a single pane of glass this large for granted. Today's modern float glass was invented by Alistair Pilkington in the mid-50s. He discovered that molten glass would float on molten lead, similar to how oil floats on water. The lead was a very toxic process, so they ended up switching to molten tin to float the modern glass on. This process turned out to be an excellent process to make large format clear glass with consistency. This technology is still used today, with a float glass factory typically producing over 9 miles of glass a day. And that's every day. These machines cannot be shut down because then the glass will harden and it will ruin the equipment. So they run basically 7 days a week, 24 hours a day. I'd like to talk a little bit about energy efficiencies that were available back in the 70s up to, let's say 2010. Energy efficiencies as they related to historic windows, whether they were restored or reproduced, were fairly limited to us in the 1970s through around 2010. We would often make wooden storms and screens for an authentic look, but more often than not, aluminum triple tracks were specified for low cost and ease of use. The development of new weather stripping materials greatly helped in reducing air and water infusion, but basically that was about the extent of what could be applied to historic windows. New to the market was the vinyl thermal pane replacement sash, and these units would often overrule historic accuracy because there was no energy efficient, historically accurate windows available anywhere on the market. So toss out the hand-blown glass and the handmade sash and install a replacement sash kit. Even though this solution lacked aesthetic value and historic accuracy, many institutions were inclined to install the new technology, kind of like wearing saddle shoes with a fine Italian suit. Low cost, low maintenance, and higher energy efficiencies were the claim of the day, absolutely zero as far as historical accuracies. In many cases, these inexpensive vinyl thermopane replacement sash kits were poorly made. They were comprised of a single seal of butyl with an aluminum spacer bar and a vinyl frame. We refer to these as an 11-year window with a 10-year warranty. Massive failures were the end result in many of the cases. This was the first big clue that there existed a huge gap between historical accuracy and energy efficiencies. In those days, words like climate change, coefficient of solar heat gain, R value, U value, and visible light transmission had not even been spoken. In addition, fossil fuels were a lot cheaper by comparison today. Today, these are the words that drive the modern window market and define how a window performs today, how a window is rated. We say that glass is the engine that drives the window. That being said, it's still very surprising how few tools today's window manufacturers have in their toolbox to make windows more energy efficient. Basically, you have gas and low E glass. And that's it. Let's talk about energy efficiencies as it relates to today's window industry. 56 million new windows were installed in 2020 with a forecast of $15 billion to be spent on new windows here in just the USA alone. Today's insulated glass units are built with a myriad of low E glass coatings. Low E is either on surface 2 or 3 so that those surfaces are inside the IG unit to keep those low E coatings protected from the elements. There are a few low E coatings that are located on surface 4 or the inside surface of the window. These coatings reflect the infrared heat back into the building with more efficiencies than coatings on surface 3. This means that any coatings on surface 4 must be designed to be rugged enough to withstand window washing with chemicals, abrasive treatments from cleaning, washing, or pressure washing the glass. In addition to utilizing low E coatings to improve the energy ratings of an insulated glass unit, or an IGU as we refer to it as, manufacturers have the option of adding gas to the space between the two pieces of glass. Currently, argon and krypton are the two primary choices that are available in the marketplace. Krypton performs much better in smaller or narrower convection channels such as quarter-inch air spaces, and argon performs better in larger air spaces such as half-inch up to a 1-inch airspace. Krypton can give a significant increase in energy ratings, but is a lot more expensive than argon. With much of the krypton being sourced from the Ukraine, krypton prices have and will most likely continue to rise. Getting back to the many low E coated glass products that are currently available on the market, we look to low E glass to do two things. In the northern climates, we want the glass to reflect as much infrared back into the building during the nighttime heating cycles. We are not nearly as concerned about solar gain, and we prize the daylight here in the Northeast. When designing for climate change, you must add back into your design the factor that it is getting hotter, and the solar heat gain coefficient must be considered. In southern climes, we want the glass to reflect as much sunlight and the associated heat back outside the building. This measurement is called the solar heat gain coefficient, or the SHGC. A very important measurement in hotter climates for creating energy efficiencies and sizing air conditioning equipment. In every aspect of window design, you give something up when you gain something. When you increase your window's efficiency with the addition of low E, you lower the amount of light that enters in the building. We measure the visible light transmission in every build design and weigh that against what we've gained. I'm sure you have walked outside of a restaurant midday only to be shocked at how bright it is outside. You immediately reach for your low E solar heat gain mitigation devices, your sunglasses. As the sun sets, you switch back to your clear glasses. This is a good example of the issues facing the selection of low E products for your windows. One last option available in today's market is triple glazing. This is an effort to reach higher energy efficiencies in your window design. Triple glazing in the conventional application produces a very heavy IG unit. This requires huge sash balances to offset the increase in weight, and the hardware usually has to be upgraded. The additional glass also contributes to more loss of visible light, but the biggest drawback is you add 100% more linear footage of seal. So basically, all that is available in the modern window industry in an effort to make IG units more efficient is low E glass and gas. In essence, we have reached a glass ceiling in the world of windows. There are emerging technologies that offer promise for new windows, such as vacuum glass or ultra-thin low E glass as a middle glazing. Similar to the glass that's used on your phone, it's not easy to wash, cut, or handle, and as a result doesn't really give you any major increase in energy efficiencies. There are some other technologies that are available out there, and we'll talk about those in the upcoming segment. So the question is, how do you build a more efficient insulated glass window? It is our current position that designing insulated glass units that integrate the Eastman's low E mylar interlayer is by a far margin the best option, especially for historic buildings. This does not offer incremental gains, but instead offers huge gains. The overall thickness of the insulated glass units is always a consideration when fitting insulated glass into a historic sash. The thinner the overall dimension of the insulated glass thickness, the better. But the thicker the overall dimension, the higher the energy efficiency. Again, you weigh out gain versus loss. The Eastman's Mylar low E interfacing is 0.003 of an inch thick, with the option of low E coatings on both sides, so thus no net effect on weight or thickness to the IG build. In addition, the Eastman inner layer has low E coatings that will not stick to glass, only to Mylar. So this opens up lots of options as you design your insulated glass units. This is a huge advantage over low E glass. The fact that Eastman's Mylar is available with several different types of coatings means that you can offer many different performance options to control how the insulated glass unit performs. This is a key point. By that, I mean you can directionally now tune a building with its windows. Now think about that for a moment. You can directionally tune a building with its windows. A good example, when designing windows for the south and west side of a building, you can specify Eastman's SC75. This particular Mylar film is designed to minimize the amount of solar heat gain coming into the building and allows engineers to specify smaller equipment. On the north and east side, you can use Eastman's TC88 film for maximum reflectance of infrared back into the building during the nighttime heating cycles, again allowing the engineers to downsize the heating equipment. Now this translates into huge savings in energy costs as well as smaller HVAC requirements. Robert Clark, a founder of Southwall Technologies, used this design to directionally tune the Empire State Building. Robert Clark replaced 13,000 windows in the Empire State Building 11 years ago, and to date there have been no issues or failures. This huge leap in energy efficiencies gave the Empire State Building a LEED Gold rating. So this begs the question, why isn't every window manufacturer using this technology? Well, first, when it first came out, like any technology, there were failures in the 1990s, all of which have been resolved. Secondly, and more importantly, everything in the modern glass industry is robotized and based on building for the lowest cost to the end user. This is a consistent trend, and we call this the race to the bottom. So with the technology that we've discovered, the question is, how powerful do you want your window to be? This is the question that consumers should be asking. How powerful do you want your windows to be? How energy efficient do you want your window to be now that we have options that are not currently available in the majority of today's window market? Unfortunately, the modern window industry has boxed themselves into a corner. With just glass, low E glass and gas to use, they simply cannot offer their consumers a powerful window, or I should say they refuse to offer that to their consumers because we found the technology and we've integrated it into our historic windows. Let's take a look at a performance breakdown of a few different window configurations. Let's start with the common double hung, single pane, putty glazed and painted window from, let's say, 1830. So take a look at the R value. 0.96 is not very good. The U value is 1.041. Visible light transmission is good in a single pane of glass, but the solar heat gain coefficient of 0.861, not that good. Now remember, the higher the R value, the better the efficiency of the insulated glass unit, and the lower the U value and the SHGC, the better the IG unit. And obviously, the lower the TVIS is, the less light you're going to get entering your home. So as you can see, the R value is not good. Now we take that same window and we add a wooden storm window to it. You can see that the R value rises fairly nicely to 2.02. The U value drops to 0.493, which is better, and the solar heat gain drops to 0.764. Notice the effect of the second pane of clear glass on the visible light transmission, with the TVIS dropping from 0.899 to 0.814. Slight drop in the amount of light transmission. So each piece of glass lowers the amount of light entering your building. Now we change that window to an insulated glass unit, which we refer to as thermopane. Still 2 pieces of glass. No storm window is required, but we add a low E Guardian 7036 to the interior pane, and we add argon between the 2 pieces of glass. The R value jumps to 2.94. U value drops to 0.340. These are both good. Visible light transmission drops a fair amount to 0.703, mainly due to the Low E glass that we used. Now we install an IG unit that is thicker, a 3/4 of an inch overall dimension. We integrate Eastman's Low E interface, the TC88 product, and we use argon gas. We use the Guardian 7036 Low E on the inner pane. Now check it out. The R value jumps to 4.76. That's a very good energy efficient insulated glass unit.
The view value drops to 0.210 and the visible light transmission drops to 0.654. And the SHGC is 0.493.
Basically, this is a very good energy efficient window, ideal for any historic application. Now we take the exact same 3/4 inch insulated glass unit, but instead of using argon, we install krypton. The R value skyrockets to 7.14. The U value drops to 0.140, which is remarkable. And notice that the visible light has not changed at all because gas does not affect the TVIS and it remains at 0.654. This is a key point when deciding which gas to use. Neither one of them will detract from the amount of natural light that enters your building. But krypton, which is more expensive, gives you a much better energy efficiency. Now we go to the next step in an insulated glass unit that is a 1-inch OD using 2 glazings of Eastman's TC88, also still using the Guardian 7036 Low E on the interior pane, and we use the krypton glass. Now hold on to your hats. The R value hits an amazing R11.36. I'm going to say that again, R11.36.
The U value drops down to 0.088, light transmission drops to 0.453, and the SHGC is 0.378, which exceeds any code requirements anywhere in the United States.
This brings us back to our comment, glass is the engine that drives the window. So, when you're trying to achieve historical accuracy in today's modern windows, we like to use restoration glass. First of all modern restoration glass that is used in the restoration of historic buildings needs to reflect the quality and look of the 4 grades of glass that were commonly used in the 19th century and the early 20th century. Glass manufacturers were not trying to make wavy, uneven glass, but instead they were trying to make clear glass with good optics. They were also trying to make glass in larger and larger sizes to develop the 1/1 or the clear view window. The first sash with no muttons in a view corridor was the birth of the clear view. Today we take that for granted and large panes of glass are now commonplace. Take for example the picture window. In today's window world, restoration glass needs to be flat before it can successfully be used to build insulated glass units. Well, unfortunately, restoration glass is not flat. It's far from it. Most of it is more like potato chips. This means that you cannot build IG units for historical buildings using restoration glass. This is the exact point where the gap between energy efficiency and historic accuracy closes. Liberty Glass Company is now making wonderful flat restoration cylinder glass in large formats, currently up to 9 feet by 5 foot sheets of restoration glass. Additionally, tempered restoration glass, laminated restoration glass, safety glass, and hurricane security restoration glass is now available for the first time. Now this is where it gets really interesting. Once you can successfully build a modern IG unit using restoration glass that's flat, you can begin to add in all the elements mentioned to achieve previously unobtainable energy values in historically accurate, extremely energy efficient insulated glass units. This is a huge breakthrough for historic buildings of all types. Historic windows have true divided lights in the sash, meaning each piece of glass is separated by wood dividing the mutton. But that creates a very poor situation for energy efficiency. So the next step for us was to develop a simulated divided historical window that reads as an original true divided light sash. We are now able to alter the individual view corridors in a simulated divided light and emulate the look and feel of true divided light with super energy efficient historical glass design and build. So I'd like to talk about a few different case studies because they're very interesting. And we found that every historic building needs a slightly different scope of work to address the different conditions that exist. So I'd like to start with Connecticut Hall, which was the first building constructed at Yale in 1750 and is the very last surviving original 18th century building on the campus. This magnificent building was fortunate to have all of its original solid stock mortise and tenon window frames and about 85% of their original sash. About 15% of the original 12/12s had been changed out for the later 6/6 sash with the larger glass panes, as glass became available in that size around 1820. So when the time came to restore the sash and frames, a great attention to detail was required. Originally built as a dormitory, revolutionary luminaries such as Nathan Hale, Eli Whitney, Noah Webster, they all stayed in Connecticut Hall as it was a dorm at that time. Since this building had such significant importance, Yale wanted to make sure that every single piece of wood was salvaged that we could possibly save and restore every sash, frame, and shutter to its original glory. The biggest problem facing our restoration was the wooden splines on the back of the sash that hold the small metal glazing points had split the splines from the mutton from many years of repairing the glazing and re-adding additional points. This meant that we had to repair and epoxy new wooden splines and refasten them back onto the original 18th century wooden muttons. It was delicate and time-consuming work, but the end result was fantastic. A quick look at before and after pretty much tells the story of restoring 18th century sash. In addition to restoring the frames and the shutters, we added a high-performance, low-E storm window to protect the glazing from harsh New England weather. The Cox Cage Gymnasium is the city's historic lineage since its conception in 1928. Measuring over 356 feet long and 156 feet wide, with the ceiling reaching almost 83 feet, the building encompasses over 3.3 million cubic feet of airspace. There were major renovations to the old cinder track and dirt floor in the skylight, but the tarnished and aging steel frame windows had endured decay and disrepair for 93 years and were in need of some serious restoration. We decided to renovate all 30 existing steel frames at Cox Cage. These frames combined have a net surface area of over 15,000 square feet, including the replacement of all existing single pane glass with approximately 7,000 panes of energy-efficient, low-E laminated glass. We worked with Guardian Glass to manufacture a laminated glass which has the low-E surface on surface 4. This is their IS-20 low-E product, which was perfect for this project, the perfect solution. By designing the low-E on surface 4, the infrared did not have to pass all the way through the glass and hit surface 3 before the reflecting started, and that allowed the heat to come back into the interior space, adding maximum energy efficiency to the design. Each steel window is composed of individual steel frames. These sash were carefully removed from the building envelope, transported to our facilities in North Stonington to undergo a thorough 10-step restoration and renovation process. Once reinstalled, each window was required to pass a rigorous on-site rain test procedure to ensure final certification. The end result was fantastic. The combination of the renovation to the building and the new high-performance glass made the building look spectacular once again. Woodbridge Hall is a limestone Beaux-Arts building designed by John M. Carrère and Thomas Hastings. Both studied at the renowned École Nationale Supérieure des Beaux-Arts in Paris, before apprenticing at the firm of McKim, Mead & White. They went on to design many distinguished projects like the New York Public Library, the Ponce de Leon Hotel, and St. Augustine. So Woodbridge Hall is a beautiful building reflecting their skills. Woodbridge Hall was completed in 1901 and stands as an architectural gem on Yale University's campus. Cooper Historical Windows' goal was to find a solution that would preserve the historical accuracy while upgrading the energy efficiency of the 26 original large double-hung windows. The first and second story double-hung windows housed large panes of original cylinder glass. The original cylinder glass is some of the finest examples of this glass that we've ever come across and had the original wood stops, So they used wood stops instead of the typical putty glazing. This allowed us to replace the original deteriorated wood stops with new Akoya wood stops. Akoya is a plantation-grown pine and a renewable resource that goes through an acetylization process. This process changes the molecular structure of the wood so it does not react to the hydrogen molecule. This means that the wood does not absorb or give off H2O. This means the wood does not expand or contract with local changes in humidity. This makes Akoya the ideal wood to use in historically accurate window and door replication. The windows were documented, numbered, and carefully removed and put through an extensive glass-out restoration process to restore the sash to their original state and offering a long-term solution. In addition, before the restored sash were reinstalled, the frames were abated of lead paint and asbestos caulk, and new backer rod and caulk was installed, and they were then painted with an Italian water-based polyurethane paint. Since the sash did not originally have putty glazing but instead had wood stops, we didn't have to worry about exposing the glazing to the elements. This allowed us to design the project so that we could install interior, high-performance, low-E glass storm panels. This allowed the original sash to look exactly like they did when the building was built. The two types of basement windows were large, double-hung sash and awning-style windows, which had deteriorated beyond repair. So we replicated the original windows using the Copen pattern details and reusing the original hardware. We built a thermopane insulated glass, or IG unit, with historically correct glass that we manufactured in-house, matching the existing original glass. For the interior glass, we used a specific high-performance low-E glass to reflect the heat back into the interior space, and also selected it for its good light transmittance. Woodbridge Hall is a prime example of taking a historic treasure and not only restoring it to its original state, but enhancing it to be enjoyed for many years to come.